Focus. Are we focused? Not you, I mean the camera. Hang on. Well, it'd be good if we both were. Ooh. Focus. Hang on. Ooh. I think I'll edit this out. Although, having said that, it does have a certain charm, doesn't it? Yay! Magic stuff. Okay, well, I wasted a bit of paper. Good stuff. Sorry, I said it was an LCR circuit in the last video. It's not. It's an LC circuit. It makes life that much easier. So it's part C of A1 part 3. And again, yeah, we're just trying to prove that this system, like the mass, like the pendulum, all obey simple harmonic motion. Which is this equation here. Yeah, cool. Okay, so again, first thing we do every single time we've got a system we can visualize is to draw a diagram so we can properly get into it. This one's slightly harder than the other one because we can't actually see what's going on because it's kind of an electric circuit and it's slightly less intuitive. But still, we should have something that looks somewhat like this, where we have a current flowing round, we have a capacitor, and we have an inductor. Okay, so for this one we have to employ Kirchhoff's second law, which is just saying that kind of the voltages in a circuit all have to add up to 0. So let's make sure that's tuned now. I'll just, whoops, the daisy. Ironically, while talking about electricity, my phone's saying it's low on battery. Hopefully we'll make it to the end of this one. So yeah, Kirchhoff's second law just says that all the voltages have to equal 0. So that's the voltage of the inductor plus the voltage of the capacitor equals 0. Okay, cool, because, yes, well, because if this doesn't seem to make sense, one of them is obviously negative. The voltage through the inductor is going to be positive and the voltage through the capacitor is going to be negative. I hope, I think, maybe not. Oh well. Anyway, so let's put these equations down. VL is just L times by, so that's the capacitor times by kind of the rate of current through it. Again, these are just kind of standard equations. Hopefully we should know by now. Yeah, so that's just di over dt. So the voltage is proportional to both the inductance and the rate at which current is flowing through it. And then Vc, the voltage of the capacitor, is, again, nice simple equation. It's just charge over capacitance. So we can pop these two, put 1 and 2 into this equation here. So we get L di over dt plus Q over C equals 0. Now, hopefully, some of the eagle-eyed among you will know that I and di over dt and Q are related. In fact, it's dq over dt, which equals I. So what we're going to do to the entire system now is we're going to differentiate both sides with respect to dt, so that we can employ this handy equation. So we put d over dt of L di over dt plus q over c equals d over dt 0. Let's do the right hand side first. So the right hand side, the derivative of 0 with respect to time is, no prizes for knowing, it's 0. And the left hand side, we're going to do this a bit more thoroughly this time. I think it's important to do this because a lot of the time, actually, in oscillations and when you've got orbital stuff later on, we'll talk about that later, it's really important that you don't assume anything with differentials, that you differentiate the whole thing properly. So we've got dl over dt times by di over dt. So we're just doing the differential of this times by this plus the differential of this times by this. I think it's is it differentiation by parts? There's a no, it might be there's a good name for it. Anyway, we're doing some basic differentiation. So now we keep the L the same, but we differentiate this one over dt plus, again we have dq over dt times by 1 over c plus q times by dc over dt. Okay, cool, and that equals 0. Now, what we'll do is we'll just branch those off so we know what we're talking about. We've got four kind of parts of this equation, and some of them are cancelled quite nicely. Hopefully you should already see which ones those are. The inductance of the inductor is independent of time. It's got no time function to it. So naturally we can take this guy out. This equals 0. And so we can get rid of this whole bit here, which is rather fun. And secondly, the capacitance isn't dependent on time in this equation. So again, this just equals 0, and we can get rid of this whole section here. Okay. Lovely stuff. Oh, we have to move on to the second sheet, first time for everything. So we have L d squared I over dt plus this section here, which is dq over c dt, and that equals 0. Okay, we're going to employ our equation we had all the way up. Oops, so all the way up here, which again should just be a known quantity, a known thing, and that's L d squared I plus I over c equals 0. Okay, already we're looking rather smashing. Let's divide by L and make just change a few symbols around there, just so we know the second derivative of I with respect to t is just I double dot. We're dividing by L, so we get I over LC equals 0. So we know that W squared equals omega squared equals 1 over LC. So we can just square root the whole thing and get that omega. Well, the frequency of the simple harmonic system is the square root of L over C, and I hope you'll agree that that equation is the same as the one we were trying to get out. Phew. Excellent stuff. Well, that's all very pleasing. Yeah, that's passing.